Assalamualaikum brothers and sisters. So in the last video, we have covered PN junction diode in reverse bias mode and in forward bias mode. In forward bias, we have covered the equation of the diode current, and the diode current and the diode voltage has an exponential relationship. Okay, so if you want to do a DC analysis of a circuit that contains a diode, it is easier if you represent the diode using one of these three models. I will explain why in the next few slides. So the first model is the ideal case diode, at which the diode will become short circuit when it is forward bias. Okay, and when it is reverse bias, your diode will be open circuit and there is no current flow, because you can see this region, the diode current is 0. So diode is open circuit during reverse bias. But during forward bias, when there is current, your diode will have a value of 0 volt. Okay, so a voltage of 0 volt means a short circuit. Alright, so that's why your diode becomes a short circuit when we use model 1. For example, in this case, you can see the question asked to calculate the diode voltage and the diode current using the ideal model. Alright, so your diode will change to a short circuit here, you can see there, and you just do the KVL, the current equivalent to 2.5 milliampere. The voltage across the diode is 0 because it's a short circuit, and the question also asked to calculate the power dissipation. Power is equivalent to IV, so VD multiplied with ID equivalent to 0 watt. Okay, so that's model number 1. Another model is known as the piecewise linear model or model 2. For model 2, basically the diode needs to have an equivalent turn-on voltage of V gamma in order for the diode to be forward bias and to allow current to flow. Alright. In the case of when your power supply is less than V gamma, which is this region, okay, your diode current is 0, which means that the current cannot flow and your diode is open circuit. And if you do your KVL, your diode voltage is equivalent to minus Vs. Okay. However, when your Vs is bigger or equal to V gamma, your diode will turn on, okay, and it will take the value of a constant battery equivalent to V gamma. Because of this straight line here, it means that your diode takes a constant voltage value. So it will convert into a battery when it is forward bias, right? So if you use the same example just now, and the question mentioned using constant voltage model, and the question gives you what is V gamma, it means that you are going to use model 2. So based on that, you change your diode into a battery, as you can see here, and do your KVL again. Alright, and this time you need to include V gamma. So IDR plus V gamma minus 5, and then you can find what is the diode current. So the voltage across the diode is the turn-on voltage, 0.65 volt, and the power dissipation is just the calculation IV, and you will get 1.414 milliwatt. Okay. However, in order to make the model for the diode to be a more realistic interpretation of the exponential relationship, they decided to use another model called model 3, piecewise linear model, where this time there is a slope. You can see here, instead of a constant voltage, there is a slope. When you have a slope in a current voltage relationship, it means that you're going to have resistor. So during reverse bias, again, when your power supply is less than V gamma, your diode will become open circuit and there is no current. However, this time when your Vs is bigger or equal to V gamma, instead of converting into a battery, it will convert as a battery with a resistor RF, okay, because of this slope here, right? So the value of VD will be equivalent to the voltage across this branch, IDRF plus V gamma. Okay, so if you look at the same example just now, this diode will change into a resistor and V gamma. If you look at the question, it will give you what is V gamma and also RF. So you know that you're going to use model 3. Therefore, just do KVL again, alright? And you're going to get the diode current. And this is the important thing. Okay, VD is equivalent to V gamma plus ID RF. For model 3, you need to include ID RF because it is part of the diode. So therefore, VD equivalent to 0.682 volt. So the power equivalent to diode voltage multiplied with the diode current. Okay, and you will get the power dissipation. So why do you need to use all these models? Okay, it is because, let's say if we do not have these models and we use the formula here, and if I do my KVL as usual, so VPS equivalent to IDR plus VD, and I replace my ID with this equation here, alright, I will have VD in the exponential equation and another diode voltage unknown here. So I need to use iteration method in order to get the value of the diode voltage, which is going to take a long time. And once I get the value of the diode voltage, then only I can calculate what is the diode current. So it is because of the time consuming mathematical operation that these models are created for the analysis. So I have this table here where I compare the three models, okay, the ideal model, model 2, model 3 with the direct approach, and you can see that especially these two models, the values can be used as approximation. Alright, so let's look at one example. So you can see in this example that the circuit structure is not straightforward, where you can see the loop and you can do the analysis straight away. But this is a common circuit structure for electronics. The first thing you need to do is to identify the nodes. So how many nodes are in the circuit? There are two nodes, node A and node B. Alright, let's identify the components in the circuit. You have power supply 9 volt, you have the 10 kilo ohm, 20 kilo ohm, the diode, and the 20 kilo ohm, and don't forget the ground. So you need to make sure that the ground is always at the bottom here. Alright, so just imagine you bring that 9 volt supply to the left like this, and it is connected to the 10 kilo ohm. Alright, okay, and the negative terminal of your power supply is connected to ground. Alright, this 10K here must be connected to node A, right? And node A is also connected to this 20 kilo ohm, which is this one. So I just connect node A to the 20 kilo ohm, alright? And the 20 kilo ohm is also connected to ground as follows. So my node A here, alright, is also connected to the diode, and the diode is connected to node B. Okay, and node B is connected to this 20 kilo ohm, which is this one, and it is also connected to ground directly. So this will be where your voltage will be measured from node B to ground, and this is my node A, okay, and this is my node B. Alright, so now you can see a proper loop for you to do your analysis. So for example, let's do mesh analysis. Okay, so this is the circuit just now, and we have established that this is your node A and node B. This is the current I in the question, and the voltage is measured between node B and ground. Okay, so the question gives you the turn on voltage V gamma to be equivalent to 0.6. So when the diode is turned on, it will convert into a battery equivalent to 0.6 volt. Okay, so since I want to do mesh analysis, I will define this loop. Okay, and I will call this loop 1, and this loop I will call this loop 2. And you can see from this loop, I2 is equivalent to the current I. Okay, so now let's do the mesh analysis. So from loop 1, the equation is 10 I1 plus 20 I1 minus I2 minus 9 equivalent to 0, and mesh number 2 is 0.6 plus 20 I2 plus 20 I2 minus I1 equivalent to 0. And I simplified mesh 1 until I get 30 I1 minus 20 I2 equivalent to 9. And similarly for mesh 2, simplified to become 40 I2 minus 20 I1 equivalent to minus 0.6. Okay, so I multiplied this equation with 1.5 so that I obtain 60 I2 minus 30 I1 equivalent to minus 0.9. And I add this equation and this equation, that I obtain 40 I2 equivalent to 8.1, and I will get I2 equivalent to the current I, 0.2025 milliampere. After that, just use Ohm's law, because the current flowing through your 20 kilo ohm here is the current I, and V equivalent to 20 I2, which is your current I. equivalent to 4.05 volt. So that's how you can analyze a diode circuit. The only electronic part is converting your diode into the model, and the rest is just basic circuit. Okay. So next, let's look at the DC load line. So a DC load line is referring to the linear equation y equivalent to mx plus c. So in order to derive the equation, you need to plot ID versus VD. So in order to get the equation, you need to do your KVL here at this loop, which means that the equation will be minus VPS plus IDR plus VD. And then you need to rearrange to make ID to be equivalent to your Y, and then VD to be equivalent to your X. Then VS over R will be your Y intercept. And then your slope M will be equivalent to minus 1 over R. So for this example, after we did our KVL, we rearranged the equation and we got this equation. ID equivalent to minus VD plus 5 over 2. So this will be your y-intercept. Okay? And minus 1 over 2 will be your slope. So the negative sign indicates a negative slope. So basically, in order to know what is the x-intercept, so you need to set ID to be equivalent to 0, and therefore you can get VD equivalent to 5 volt. Okay? So if you notice, this 5 volt is actually your VS. That's the x-intercept. Right? Okay, so the next thing you're going to do is to complete the structure of the load line is plot this line here. Okay, this line, and this is where the VD value, okay, that you have calculated, and then it will turn on, and this is the Q point, the operating point. So what is the value of ID at 0.62? Okay. So basically, when you put in 0.62 in this equation, okay, so you're going to have ID equivalent to minus 0.62 over 2 plus 2.5. So that's what you get here, 2.2 milliampere. Okay, so that's how you compute the value of diode current once you know the value of VD. Okay. So if you can see for this example, the question gives you the load line and you are given the circuit. So you are asked to design. You are asked to design means you are asked to find what is R. Okay. So the diode is operating in forward bias condition. So you are asked to determine the diode current ID and RF. Okay. Using the piecewise linear model, consider the cut-in voltage of the diode V gamma is 0.65 volt. So the question asks you to find RF, which means that you are going to use model 3. Okay. So firstly, you need to do is derive the equation. So when you derive the KVL equation, so you will get this equation here. Okay, you will get IDR plus VD minus 5. Okay, and then please rearrange the equation to become Y equivalent to MX plus C. So make sure your Y is ID and the X is VD. Okay, so after that, you know that 5 over R is your C. So 5 over R is your C and the value is given here, 2.5. So that's why I put here 5 over R is 2.5 milliampere, and I managed to get R equivalent to 2 kilo ohm. Okay, so that's done. Now, what's next? Finding your RF kan? Okay, so you know that you're going to do your model 3. Okay, please take note that this point here is VD. Okay, okay, so I put that at VD equivalent to 0.7. Use the equation here to calculate your diode current. And we need to calculate your diode current because we are using model 3. So model 3, the value of VD is equivalent to V gamma plus ID RF. Okay, V gamma is given. Okay, so V gamma is given as 0.65. This is how you can find the value of RF because 0.7 is given here as VD. V gamma is given in the question just now, 0.65, and you already calculated ID. So RF is equivalent to 23.3 ohm. Okay, So that's how you can solve a design question when you are given a load line and a circuit. Remember, the first thing you need to do is to do the KVL and get the equation of Y equivalent to mx plus c. The approach is always the same. Okay, in any design question, just do the step by step and you will be able to solve it. Okay, so next is going to be the multiple diode circuit. Okay.